but there's been a new cosmic microwave background measurement, so something called the Planck satellite. And this satellite has really improved the maps of the cosmic microwave background. And it's a really interesting result, but for the most part, the results look to be consistent with our so-called lambda CDM universe, where if you look at the energy distributions today, most of it is dark energy. Then you have dark matter, some visible matter in the form of baryons, and then a little bit of radiation. So kind of the standard dark matter, dark energy picture seems to be holding up well. As Tibor said, we don't have to cancel the course, so dark matter still seems to be there. There are a few puzzles with the results, but the dark matter side of things seems to be pretty good. So you'll probably be hearing more about this in the next few days, because it's a really interesting, really improved measurement. But as far as this course goes, dark matter still seems to be there. In fact, the density they find is a little bit bigger than before. So let's go on to calculating. OK, so remember, we're doing dark matter thermal freeze-out. And what we're computing is we're starting off with dark matter in full thermodynamic equilibrium in a hot early universe. And then as the universe cools, we're calculating how this dark matter falls out of equilibrium. And this is going to let us compute what the final dark matter density is. So remember, to compute this deviation from equilibrium, we have a Boltzmann equation. So I'm going to write it as dn chi dt plus 3h n chi, where n chi is the dark matter number density. And this is equal to our collision term, where the collision term accounts for reactions. And for example, suppose my reaction that changes the number of dark matter is chi goes back and forth to a standard model fermion. Let's say FF bar. This reaction, the collision term for it, or at least the contribution to the collision term from this reaction, is just minus integral d pi chi1, d pi chi2, where these are the phase spaces. And then I also integrate over the phase space of the final states. And we have our usual delta function that conserves overall energy and momentum. And we have the matrix element. And then we have the distribution functions of the particles minus the distribution functions of the final states. So this is the thing we want to compute today. And we're going to compute it, or we're going to take this and massage it into a slightly nicer form by making a few a few approximations and a few pretty good assumptions. I'll come back to justify some of them. And one of the assumptions I'm going to make is that these collisions, and I'll come back and justify this a little bit, but that these collisions keep the dark matter particle in equilibrium until after the temperature falls below the mass of the particle. The other thing I'm going to assume is that when the dark matter particle falls out of thermodynamic equilibrium, it still stays in kinetic equilibrium. And again, I'll come back a bit later and justify this assumption as well. OK, so in any case, this is our collision term. And we want to write it in a way that is a bit nicer. And for this, I'm going to make a couple of approximations that turn out to work pretty well. The first of them is that these the first of them is that I will assume that these guys are standard model fermions, and they're pretty light. And these guys are in equilibrium. Yes, Tibor?
So you said something like when they fall out of thermodynamic equilibrium, they're still in kinetic equilibrium.
Yes.
Sorry, I was under the impression that the kinetic equilibrium was a special case of thermodynamic.
No, OK, so full thermodynamic equilibrium means that you have the right energy distribution. And remember, for us, the right energy distribution corresponds to this grand canonical ensemble thing. But a second aspect to that is having the right number distribution. So the grand canonical ensemble predicts two things. It predicts the distribution of states with energy, but it also predicts a number density. And so there are two aspects of this equilibrium. The kinetic aspect is that the relative distribution of states with different energies follows the shape of the grand canonical ensemble. But the second thing is, and that corresponds to kinetic equilibrium. The second aspect, chemical equilibrium, is that the number density matches up. So the kinetic part means that suppose I have a distribution function as a function of energy. And I'm trying to get some colorful chalk here. Suppose this is the grand canonical equilibrium distribution. In kinetic equilibrium, in kinetic equilibrium, I'm going to have the same energy distribution, but the overall normalization might be different. On the other hand, when I deviate from chemical equilibrium, when I deviate from kinetic equilibrium, I can have a different shape. So this is full equilibrium. If I only have kinetic equilibrium, suppose I have, I essentially just take this and rescale it by some factor. So we're going to assume that we have kinetic equilibrium, but kinetic equilibrium doesn't necessarily mean that the total weight here is right. So I can have different number densities. Okay, so that's the first thing. The other thing I'm going to assume are that the standard model fermions, these F and F bar, are in thermodynamic equilibrium. And this should be a good approximation as long as the dark matter particle is fairly heavy and the dark matter freeze-out doesn't happen at too low of a temperature. So we know that to a pretty good approximation, stuff in the standard model equilibrates pretty well with the photons. So I'm going to assume that these guys are in equilibrium. And the last thing I'm going to assume, or actually two other things, I assume these guys are in equilibrium with effectively a zero chemical potential. And this will also be a good approximation. We know that standard model fermions do have a non-zero chemical potential today because we see more matter than antimatter. And a non-zero chemical potential corresponds to an asymmetry between matter and antimatter. However, the size of this chemical potential is really small compared to the temperatures at which this stuff is occurring. So this is going to be just a tiny, the non-zero value is going to be a tiny deviation. So it's a good approximation to set that to 0. Finally, the other thing we're going to do is take our actually it's a typo in my notes, but we're going to approximate our full quantum distribution functions by just Boltzmann factors. And it turns out that this is a reasonable approximation as well. Now, what we get out of this is that given these assumptions, our distribution functions for the fermions, the F and the FF bar, are just going to be e to the minus EF plus EF bar over T. And because we have energy conservation through the delta function, this means that we can change these guys to the sum of the energies of the dark matter particles, E1 and E2. So in other words, because for every contribution in this collision term, I plug in the initial energy momentum of my two dark matter particles and the energy momentum of my standard model particles. And those values go into this matrix element, and they go into these distribution functions, which are functions of those energy momenta. But because I have this delta function that enforces energy and momentum conservation, the sum of the standard model energies is equal to the sum of the dark matter energies. And what I get out of this is this sum of dark matter energies is just the equilibrium distribution functions of the dark matter particles. So, yes, question?
So don't we expect that to be a really bad approximation because we've assumed the temperature is so much higher than the typical energies and masses of the fermions here? So they're very relativistic. So I mean, you don't want to use the non-relativistic limit.
Yeah, it's a bit of a cheat, but so for example, if I look at the number densities, I compute for bosons versus fermions using the full formula.
Yeah.
The difference between changing a -1 to +1 is to give me an overall factor of 7/8.
Oh, okay.
So it turns out that when you integrate over everything,
Right.
it's not too bad. So yeah, it does. I agree, it looks funny, but numerically, it turns out it's a small twist. But the upshot of all that is we get this nice relation that instead of having some weird thing here, we reduce to having distribution function ff.
Oh, right. But are we going to use the non-relativistic limit of f1 and f2, or I guess this limit we take here?
Well, we haven't gotten that far yet.
Okay.
But ultimately we will. But well, actually, it's not going to matter.
Okay.
We'll actually use the full energy expression.
Okay.
All right. OK. So now if I take this and I plug it in here, and I use the fact that when I integrate over the final state phase space with a matrix element and with this delta function, this thing starts to look like the formula you should be familiar with for cross sections in quantum field theory. So if I take that and I plug it in, what I get is delta C tilde is equal to minus integral d pi 1, d pi 2. One other thing I can do is now that I've transferred the dependence of this term onto energies of E1 and E2, I can, the stuff that goes in here now doesn't depend on these final state energy momenta. And I can actually factor the whole thing out. So I can now write this whole thing in a suggestive form. F chi 1, F chi 2, minus F chi 1 equilibrium, F chi 2 equilibrium, times a factor, d pi f bar, delta function, with my matrix element. And this piece, this piece is just like what you should be familiar with from your quantum field theory course when you compute cross sections. And this is equal to, this is a lot of shock. This thing is equal to sigma v. I'll tell you what v is in a second, times 4 E1, E2. And I have to put in a g chi squared, where g chi is the number of degrees of freedom of chi. So the slight twist here is, remember, in this expression, we have averaged over both the initial and final states, whereas in a cross-section, you average over the initial states and sum over the final states. So to make that up, we have to multiply back in by g chi squared. The other thing is that this v corresponds to what you would measure as the relative velocity of the two colliding particles in the center of mass frame. And specifically, this v, it corresponds to relative velocity, is just p1 dot p2 squared minus m1 squared m2 squared. OK, hope you can. This is unfortunately placed. OK, well, so I'll raise the board in a second. E1, E2. That's not helping. OK, so this is a 1 over E1, E2. It's in my notes. But all this represents is a dimensionless velocity. And it corresponds to the relative velocity of the colliding particles. OK, so this is nice. I now have these distribution functions. with a sigma v and a thing that looks like my usual cross-section formula that's a function of the initial colliding momenta. And I have these energies in g chi-squared. So this is starting to look pretty good. Now, one more thing, one other assumption, and I'll come back and justify this in a second. Our additional assumption is that throughout the freeze-out process, whenever we care about this collision term, we are going to be in kinetic equilibrium. So kinetic equilibrium implies that my distribution function as a function of energy is equal to some constant that depends on time times the equilibrium distribution function. So the reason this is nice is that when I go back here, when I go back to my distribution functions, these things are just going to be some functions of time times the same functions as I have here. So they don't quite cancel if that function of time isn't equal to 1. I'm not in full equilibrium, but I'm close. So the upshot of that is that if I know the energy dependence of this function, and I do if I assume kinetic equilibrium, which I'm going to justify in a few minutes, that means that if I know what the energy dependence here is, and this is some function of energy, I can do these integrals. Or at least I can rewrite these integrals in a nice way. And the result of all that is what I get out of this whole thing is n chi squared minus n chi squared equilibrium with a minus sign and something I'll call sigma v in brackets. So the sigma v in brackets corresponds to a thermal average. And what I mean by a thermal average is suppose I have any function of the energies of two particles. The thermal average of anything that depends on these two thermal average objects is given by 1 over n1 eq, n2 eq, integral d3 p1 over 2 pi cubed, d3 p2 over 2 pi cubed, g1, g2, f1 eq, f2 eq, and then whatever my object is, that's a function of p1 and p2. So all this represents is I take some quantity that depends on energy and momenta in the thermal bath, and I average that quantity over all possible momentum states. So for particles, I can label any particle state by its momentum. Here, I sum over all possible particle states, but then I weight that sum over particle states by the distribution functions. So, for example, in the case where this is the unit operator, this integral over f1 equilibrium with g1 gives me n1 equilibrium. The integral over this with g2 over d3p2 gives me n2 equilibrium, and I just get 1. So the thermal average of the unit operator is equal to 1. So that's a nice sort of thing I would like for an average. But what I'm doing here is instead of plugging in 1, I plug in this cross-section. And plugging in the cross-section gives me the thermal average of the cross-section. So physically, what this represents is the average value of the scattering cross-section for this process chi goes to ff bar in the thermal plasma, assuming it's in thermodynamic equilibrium. So this is nice because what I've done is I have some particle physics object that's been convolved with the equilibrium distributions, and I factored out all the deviations from equilibrium into this prefactor. So remember, this thermodynamic average is over the equilibrium values. So now I can go back to my differential equation. And in general, this C tilde is going to have contributions from all possible reactions that change the dark matter number density. But for now, let's just assume that the only change to the dark matter number density is from this reaction. When I take this result and plug it back in here, I get I'm going to get a new board for this. I think I've just figured out how this works. Have I? I don't know. So when I take this result, I plug it back in here, I get my freeze-out equation. And this is going to be sort of a master equation for us. We have dn dt plus 3h n chi is equal to minus some cross-sectional thing times n chi squared minus n chi equilibrium squared. So I claim that this equation has all the properties we would expect for something going in and out of thermodynamic equilibrium. Yes?
Sorry. The last line you get from doing an integral, so how do you get that? I mean,
OK, so actually, I think I actually have the class derived this on the homework.
okay.
But basically, what's happening is that, remember, these d pi integrals,
Right.
the d pi is going to be a d3p over 2 pi cubed times 2 times the energy.
Oh,
So the energy factors cancel with here. So these energy factors cancel the energy factors here to give me stuff like this. And the other thing is, as far as this stuff goes, I can rewrite this as I can factor out my zeta of t and move that out front, do the integral, and then bring it back and make either equilibrium or regular n. So you'll do this for yourselves, but it ends up working out fairly straightforwardly. And this is the final result. And this is going to be an important result for us, so I'm going to put a nice fancy orange box around it. And this is basically our freeze-out equation. So we're going to solve it, at least in an approximate way, in a second. In principle, you can just stick it on a computer and solve for it numerically. It's just a differential equation for a function n chi. The number density of the dark matter particles is a function of time. But let's just look at it. Let's just look at it in sort of an intuitive sense. So first of all, suppose this term is really, really big. When this term is really, really big, and let's say I ignore this, when this term is big, what it does is it drives the number density, dn chi dt, to the equilibrium value. So for example, suppose this is a big number and it's constant, the dn chi dt gets driven to the equilibrium value. So the exponential push of this term is to push this to this. And in fact, I reach a steady state of dn chi dt is equal to 0 when n chi is equal to n chi equilibrium, if I ignore this term. On the other hand, suppose this term becomes very small. When this term becomes small compared to this term wins. And the solution to this equation is just the number density dilutes as a to the minus 3. So let me write that down. When this term is big, and by big I mean this term beats out this term, that implies that n chi is driven to the equilibrium value. On the other hand, when this term is bigger than that term, what I get from this differential equation is dn chi dt is equal to minus 3. And remember, h is just a dot over a times n chi. And this means that I can integrate this equation easily. I just move the n chi down here, put the dt up here. The dt's cancel, and I just get a dA over a with a minus 3. And the solution to this equation is that n chi is proportional to a to the minus 3. So this is the behavior we roughly expect. In the limit when this collision term is big, I'm driven to the equilibrium value. When I turn off this term, instead what I find is that my number density satisfies this simple equation, and my number density just dilutes as a to the minus 3. And this is what I would expect if, suppose I started with a box of, let's say, 1 meter by 1 meter by 1 meter, and I put in a fixed number of particles. As the universe expands, those particles are going to move apart, away from each other. But I don't create or destroy any of those particles. And as the universe expands and that box dilutes, the number density of particles in that box that's expanding goes as (e⁻3). So this is just a dilution of particles with a cosmological expansion when there aren't any reactions to change the particle number. Now, what's going to happen, and I'll come to this numerically in a second, but what's going to happen is that suppose we look at this term. At high temperatures, and by high temperatures I mean roughly greater than the mass of the dark matter particle, we have n-chi equilibrium going like T cubed. And for the most part, we're going to worry about this happening during radiation domination. So during radiation domination, we also have H going like T squared over m Planck. So I'll just put this in a box. So at high temperatures, this n-chi going like T cubed is pretty big. Yes?
I don't understand the argument for when the right-hand side goes to is big compared to
Sorry, when the right-hand side is big?
the first argument, like when it's big. Yeah, I don't understand why n has to go to any.
Okay, well, so suppose I just have this equation,
Yeah.
and suppose that this is just some constant.
Yeah.
Then suppose I start with suppose I start. Okay, well, so first of all, if this is a constant and I don't have this, then there's a steady state, and the steady state is that this derivative vanishes and n-chi is equal to n-chi equilibrium. So in other words, this equation is consistent with this side being equal to 0 because the number density is constant, and this side just having n-chi equal to n-chi equilibrium. So
You're saying that's the only solution.
No, I'm just saying that there's a steady state that looks like that. Now suppose I start with a number density n-chi that's larger than the equilibrium value. What happens in that case is that when this is high, this is a positive number, and I have a minus sign here. And that means that if I start with this higher than this is a negative term. And the negative term means that my number density decreases. And my number density is going to decrease until the number density asymptotes to the equilibrium value. On the other hand, if I start with a low number density, I get a negative number here. The negative cancels this negative, and that means that I get a positive derivative. And that means the number density is going to increase until I hit the equilibrium value. So in other words, I can draw stuff for this. So suppose I have a system where suppose my n-chi equilibrium is just some constant. So first of all, if n-chi is equal to n-chi equilibrium, I just stay on this line. On the other hand, if I start off a little bit big, my derivative is going to be negative. So that means that I'm going to be on a decreasing trajectory. And this decreasing trajectory is actually going to asymptote to the equilibrium value. On the other hand, if I start small, I get a negative number here. The negative cancels the negative, and I get a positive. So I get a positive slope, and I'd also asymptote towards the equilibrium. So the point is that this equilibrium solution is an attractor of the differential equation, in that if I start away from the equilibrium value, I evolve towards it. So it's a bit more complicated in practice because this thing also varies with time, but basically I just take this picture and instead of asymptoting to this constant value, I asymptote to whatever it is as a function of time. So that corresponds to ignoring this piece. When I ignore this piece, I just get to this (e⁻³ dilution. Okay, so that was a bit of an aside. But actually, thanks for asking me. So I hope this asymptoting idea is clear to everybody. Okay, in any case, at high temperatures, my number density goes like T cubed. And with my number density going like T cubed, this term can end up being pretty big. So I'm going to assume that this term is pretty big when the equilibrium value is about T cubed. And the upshot of this is that I'm in the first limit, limit 1, n chi goes to n chi equilibrium. So the right-hand side can be relatively big at high temperatures. On the other hand, at low temperatures relative to the mass, so when the temperature is less than roughly m chi, in this case, the equilibrium density goes like e to minus m over t, m chi over t. And when this happens, when the number density starts going like e to the minus m over t, these number densities over here, assuming this is tracking equilibrium, this thing gets really small. And when this thing gets really small, this term gets small. And eventually, this term becomes so small that it gets beaten out by this term. And when this term gets beaten out by this term, I start deviating from equilibrium. So this term becomes smaller than this, and I'm no longer driven to equilibrium. Instead, I'm just driven to a dilution by a to the minus 3. So let me draw a cartoon of this. I want let me draw a cartoon of this. So I'm going to normalize my number density of chi by a cubed. So I'm going to plot this as a function over 1 over t. So remember, as time increases, the temperature decreases. So you can think of this axis as corresponding to time, or time to some positive power. On this axis, I have the number density times a cubed. And when I put this together, remember as well that for the most part, a goes like 1 over the temperature. So this n chi times a cubed, I'm going to start off, and here's 1 over m chi. I'm going to start off pretty high, and I'm going to be roughly constant. So at very high temperatures, corresponding to small 1 over t, my number density is going to track the equilibrium value. And tracking the equilibrium value means that the number density goes like t cubed. So when I multiply t cubed by a cubed, I just get a constant, or approximately constant. So I start off being roughly constant, and this corresponds to equilibrium. Now, when the number density falls, when the temperature falls below the mass, or 1 over t becomes larger than 1 over m, what happens is I pick up this exponential suppression factor. So let me get my colorful chalk. So in yellow, I'm going to draw the equilibrium density. So the equilibrium density, as the temperature falls below the mass, is an exponential suppression. So this line corresponds to n chi equilibrium times a cubed. So what's going to happen is my actual density is going to track the equilibrium density for a while. And in fact, it can even start tracking it beyond when the particle becomes non-relativistic. But at some point, this right-hand side, the so-called collision term, is going to become small compared to the 3h and chi term. And I'm going to start deviating from thermodynamic equilibrium. And in particular, I'm going to start just going like a to the minus 3. So because I'm plotting n times a cubed here, and as I deviate from equilibrium, I go like a to the minus 3, this thing is going to asymptote to just a constant. So this is n chi. So what happens is I track the equilibrium for a while until I can no longer track it anymore. And there's a reason for no longer tracking, and that is that the equilibrium density becomes exponentially suppressed. And eventually, I stop tracking the equilibrium, and I just asymptote to a constant value. So this is my n chi a cubed. So this is the real value. This is the equilibrium value. And you can see that the equilibrium value is just falling off the map. It's exponentially suppressed. It's just getting smaller and smaller and smaller, whereas my actual value just becomes constant. Yes?
So the n chi a cubed is basically constant for this, except for this brief period of time when it's represented.
Well, for the object freezing out. So yeah, so for the species when it freezes out,
Right.
it departs from equilibrium. In this case, it departs from equilibrium. Well, it's non-relativistic.
Right.
But if it had stayed in equilibrium, it would have just fallen off the map.
But it's just constant except for this brief period.
In this case, yes. Yeah. Yeah. So what I've covered here is specifically the case where the species freezes out, where the species leaves the equilibrium while it's non-relativistic. There are some cases when, if the interaction cross-section is really, really tiny, I can actually leave equilibrium while I'm still relativistic, in which case I would just track a constant here.
Right.
But I'm assuming that the cross-section is large enough that I track the equilibrium at least a little bit after the temperature falls below the mass, and then I fall out. OK. Now, obviously, here there's a transition between two behaviors. There's a transition between the equilibrium behavior and this more general behavior, this full departure from equilibrium behavior. And this point, where I go from equilibrium to non-equilibrium, is what I call freeze-out. And the freeze-out name makes sense because what's happening is as the temperature falls, I'm no longer able to track the equilibrium, and I leave equilibrium. And the temperature which this occurs, which corresponds to kind of roughly here, I'm going to call T freeze-out, TFO. So freeze-out represents a transition from tracking the equilibrium to not tracking it anymore. Now, the upshot of all this is that here, this density of dark matter is much, much larger than the equilibrium density. And this is precisely what we need for dark matter to give us a significant contribution to the energy density today. If the dark matter density just kept on tracking the equilibrium value, it would just keep falling off the map, and we'd end up with essentially nothing. Now, we need a relatively large density, so this kind of freeze-out picture is precisely what we want. OK. So I've said all that. There's one other thing I want to justify. And the one other thing I want to justify is the kinetic equilibrium assumption. So let me figure out what I want. I want OK. So I want to justify just quickly this kinetic equilibrium. Now, what you see from the Boltzmann equation here is the thing to compare for equilibrium is whether the term on the right-hand side at the top is larger or smaller than 3h n chi. And this turns out to be a general feature. If you want to do just a quick and dirty estimate of whether your process is equilibrated or not, what you should compare is the rate for that process relative to the rate of Hubble expansion. So kinetic equilibrium comes from scatterings of the form chi f goes to chi f. So for example, I have dark matter come in. It interacts with the Standard Model fermion through some unspecified reaction. Standard Model fermion goes out, and I have dark matter go out. So this is an elastic scattering. Now, the rate for this, suppose I take a single dark matter particle, and I shoot it into the plasma. And I ask, what's the rate at which this dark matter particle is going to hit stuff? Well, it turns out that the rate for the dark matter particle hitting stuff, called sigma elastic, is roughly a thermally averaged sigma v elastic times the number density of the fermion. And by comparison, the rate for this annihilation reaction, going back up to the top, the rate for the annihilation reaction correspondingly is the sigma v I had before times the chi density, approximately. So if I look at my top equation, note that I have an h n chi term, and then I have a sigma v n chi squared term. So this corresponds to the change in the total number density. But if I factor off one power of n chi, that corresponds to the rate at which a single dark matter particle either collides elastically with the Standard Model fermion or collides with another dark matter particle to produce, to annihilate into fermions. So this is my rate of elastic scattering for a single dark matter particle shot into the plasma. And this is my rate for annihilation, approximately, assuming equilibrium, for a dark matter particle shot into the plasma. Now, for equilibrium to happen, for a reaction to be equilibrated, what I need is roughly gamma should be roughly larger than the Hubble constant. Because if I take that and I plug it back into an equation like this, either this equation or something analogous to it for kinetic equilibrium, the things I compare are essentially the Hubble term to the equilibrating term. So here, if I look at these pieces, this elastic cross section is going to go like this elastic, this thermally averaged elastic piece. And by crossing symmetry, the annihilation reaction is just this matrix element turned on its side. So I expect roughly that this elastic cross-section should be roughly the same as sigma v. So what I expect is that the elastic should be roughly sigma v. And I know that the fermion, because it's light in equilibrium, goes like T cubed. Whereas this thing over here goes roughly like sigma v times T squared T times m to the 3/2 e to the minus m over t for temperatures below the mass. So remember, the equilibrium number density of chi below its mass goes like this. So the upshot of this is that this reaction stays equilibrated longer than this one, simply because this one gets an exponential suppression and this one doesn't. So a nice physical interpretation of this is, in freeze-out, is what's happening to freeze-out is I have my dark matter particles annihilating with each other. But for two dark matter particles to annihilate, one dark matter particle has to find another dark matter particle. And as the dark matter particles track the equilibrium, the number of dark matter particles floating around the plasma becomes smaller and smaller. So it becomes harder and harder for one dark matter particle to find another to annihilate with. On the other hand, my plasma always contains lots of fermions. So for my given one dark matter particle, it becomes easier for it to find a fermion at temperatures below the mass than it is for that dark matter particle to find another dark matter particle. So for that reason, first of all, because the dark matter particle has trouble finding another dark matter particle, I get the freeze out of the annihilation. But I still keep, to a pretty good, to much later, that the dark matter can still hit other fermions in the plasma and maintain kinetic equilibrium. So this is my argument that this, being bigger than this, means that the kinetic equilibrium is maintained longer than the chemical equilibrium. So even though the number density of dark matter particles is falling out of equilibrium, the relative energy distribution remains the same. Okay, so I wanted to make that argument. Okay, so this is all great. And but let me actually get to trying to solve the Boltzmann equation. And this is what you actually have to do if, suppose I have a great new theory of dark matter, but I want to estimate what that dark matter density is today. I need to sit down and compute that density for this equation. And it turns out that, well, people typically do this numerically. And you can actually buy, there are actually codes out there that will do it for you. But it's still handy to get an idea of what's going on to go over an approximate solution to this equation. And the approximate solution will be essentially, I track equilibrium down to here, and then all of a sudden I don't track equilibrium, and I just go along like that. Okay. Okay, so what do we actually have to do for solving? The first step is to find this thermal average. So finding the thermal average, you have to do a few things, but they're things you know how to do. So you calculate the usual cross-section that you would just do in quantum field theory. I compute the matrix element, and I plug it in, and I integrate over the final state phase space. You know how to do that. You should have done it millions of times. And this is just my, again, d pi f bar times 2 pi to the 4th, delta 4, blah, blah, blah. m tilde squared. Everybody's happy. Now, this object altogether, you can show is Lorentz invariant, in the sense that I'll have you show this on one of the homeworks. These integral measures turn out to be Lorentz invariant. The 2π4 delta 4 is Lorentz invariant, and everything going into the squared matrix element is Lorentz invariant. So this whole thing is Lorentz invariant, and it doesn't care about what frame you evaluate it in. Whereas here, these energies and this velocity do depend on the frame. Actually, sorry, this doesn't, but these energies do. So all of the frame dependence of this depends on these energies. But what I can do is take this thing, and this is going to be a function of P1 and P2. But because this whole thing is Lorentz invariant, we're guaranteed to be able to write it in a way that is also Lorentz invariant. Now, the only Lorentz invariant combination I can make out of P1 and P2 is the Mandelstam variable S. So I can write this as a function of f of S, where S is just P1 plus P2. Yes?
I'm assuming the particles are massless. Our architect could have used the mass of the particle as well.
Oh, yeah. So in general, it can also depend on the masses, but the masses don't change. So the only kinematic quantity, the only Lorentz invariant kinematic quantity is S. OK. So this is step one. Step two is take this result and integrate over P1 and P2 to get the thermal average. Now, this step, again, can be done in a slick way. You can take your integral over P1 and d3P1 and d3P2 that goes into the thermal average over here. And you can rewrite the integral measure as an integral over S and an integral over orthogonal quantities. So in that case, the integral over orthogonal quantities just factors out. And I'm left with integrating this over S. And that gives me the whole result. It turns out, though, that this can be a little bit tedious. So in a second, I'm going to give you an approximation that gives you about the right answer, up to small corrections. But after I've integrated this, this just becomes a function of time, which I can turn into a function of temperature through the relation between time and the scale factor and the scale factor and the temperature. And it turns out to be it turns out that it's convenient to rewrite this instead of just a function of time or temperature, write it as a function of x defined as the mass over the temperature. So sigma v is some sigma v of x. And the third step is plug this into my dn chi dt plus 3 h n chi is equal to blah, blah, blah. OK. I have this, I have this. OK, I'll just erase here.
In here is the mass of the thermal.
It's the mass of the dark matter, yes. So I'll add that. So this m is m chi. OK, so actually doing this in full generality is a little bit of a headache. There's a nice, simple approximation to this that works pretty well. So first of all, if my dark matter freezes out while it's non-relativistic, the value of x at the freeze-out temperature is going to be much larger than 1. And what's often done is people rewrite this result in, you can rewrite this result in powers of 1 over x. So x is a large number, and I can expand in powers of 1 over x and do an approximation that way. And the approximation that people often do, you don't have to make this, but it's still handy to see, is that instead of going through this whole business with S and rewriting P1 and P2 in terms of S, instead you do something that you're probably more familiar with. Instead, we compute sigma v in the center of mass frame. So remember, the center of mass frame corresponds to the two colliding dark matter particles having the same incoming momentum. Now, on the average, the relative momentum of the dark matter particles, when I integrate over everything, will be equal. But in any given collision in the plasma, I might have one dark matter particle traveling faster than the other. So my typical collision is not in the center of mass frame, but on the average, I don't have any net mismatch between the initial momentum. So when I compute sigma v in the center of mass frame, this is going to introduce a small, this is going to be an approximation, because in general, the dark matter particles aren't quite colliding in their center of mass frame. So when you do this in the center of mass frame, the other thing is I'm going to assume the dark matter particles are freezing out when they're non-relativistic. And if they're non-relativistic, I can rewrite the initial momenta of the colliding particles in a non-relativistic way. The energy I can write as just 1 plus kinetic energy. And how do I want to write it? 0, 0, m chi u, where u is the velocity of each particle. P2 is equal to m chi 1 plus u squared over 2, 0, 0, minus m chi over u. So I compute my cross-section, plug in these specific non-relativistic momenta. And then once I have my sigma v, so the second step, expand sigma v in powers of u squared. So I'm going to write my sigma v is equal to sigma 0 plus sigma 1 u squared plus dot, dot, dot. And the third part, and this is why this approximation is often handy, when I do the thermal average, the only object in these P1 and P2s that varies when I do the thermal average, the only free parameter is u. So doing the thermal average is equivalent to, in some sense, finding the average u squared. And when I do the thermal average, in this case, just corresponds to replace u squared in this expansion by 3 over 2x. So to the extent that x is a large number, this expansion in powers of u squared it converges quickly. So in other words, my sigma v, when I do the thermal average, is just my sigma before thermal averaging. But now I do a sigma 0 plus sigma 1 tilde times 1 over x, dot, 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 dot. So the tilde on the sigma 1 just corresponds to absorbing, going from sigma 1 to sigma 1 tilde, absorbing the power of 3/2. So now this approximation is a good approximation up to 1 over x. Once you hit 1 over x squared, this approximation is no longer good. So if x is big, and you don't care about corrections of size 1 over x squared, this recipe works just great. And the nice thing about this recipe is that the integrals you have to do, well, effectively, you don't have to do integrals. Instead of doing the complicated thermal average integral, which in the general case you have to do numerically, in this approximation, it's just a replacement of this u squared that I've expanded in by 3 over 2x. So this is nice. The other thing is that this expansion is so popular, people give names to this piece and this piece. So the first piece is called S wave. And the second piece is called P wave. And the reason for the names S and P is that you can show that this expansion in powers of velocity is equivalent to an expansion in powers of the relative orbital angular momentum in the collision. So remember, for orbital angular momentum, L is roughly mv. And L equals 0 corresponds to S wave. And L equals 1 corresponds to this P wave. So this result is useful because people will often talk about cross-sections that are S wave suppressed or P wave. And what I mean by that is that most of the time for a generic cross-section, this will be the dominant term, because X is kind of big. But there are some cross-sections where, because of the relative spins of the initial and final particles, you're forced to have an orbital angular momentum that's non-zero. And that means that the leading term can be the P-wave piece. So for these P-wave these P-wave cross-sections, they behave a little bit differently with temperature than S-wave ones. So in the literature, you might hear people talk about S-wave or P-wave cross-sections, and that's all they mean. When you do this approximate expansion, you have a term like this and a term like this. The expansion breaks down beyond this, but it still happens to be useful to think about it this way, corresponding to the relative orbital angular momentum. OK, so there's one third thing I want to mention. I'll just do this in a few minutes before I have to wrap up. I guess I can erase here. OK, so now I have my sigma v, and my sigma v is a function of this x variable, and I want to plug it back into my master equation and solve that. But remember, my master equation depends on time, so I want to convert time into this x variable, because at least during radiation domination, they're easily interchangeable. There's also one other thing, one other substitution that's nice, and that is instead of talking about the number density, it's usually easier to talk about the yield. And that is the ratio of the number density to the entropy density of the plasma. And the reason for doing this is that usually, and by usually, I mean that you can assume this is the case unless something explicitly happens to make it not the case. Usually, the quantity I call big S, which is equal to little s times a cubed, which is called the co-moving entropy, is constant. So in other words, it turns out that for most of the evolution of the universe, as long as stuff stays in equilibrium, the entropy within a box of size a cubed on every side is exactly constant. So the expansion of the universe is usually adiabatic, unless something weird happens. And I think in the tutorial today, you'll look at a case of something weird happening. But as long as something weird doesn't happen, this is just constant. Because this is constant, that means that the entropy density, defined as S, just goes as a to minus 3. So this is great because remember, up here, after freeze-out happens, my number density also just goes as a to the minus 3. So by normalizing my number density to S, this takes into account or when I normalize by S, this quantity is just constant after freeze-out. And the great thing about this thing being constant after freeze-out is that when I compute the value of this just after freeze-out, which is pretty easy, I can relate it to the, because it's constant, I can relate it to the value today. And because we know what the entropy density is today, all I have to do to find the number density today is take this value, computed right after freeze-out, multiply it by the entropy density today, and that gives me the number density today. So talking about this y quantity, this y is usually called the yield. Makes my life easier. essentially because it's constant for a particle that's frozen out. It gives me an easy way to compute the number density today without actually having to play any funny games. Okay, so I'm out of time today. I'll finish this up tomorrow and then get into some theories of dark matter, and specifically theories of dark matter that undergoes thermal freeze-out. And I think you have a tutorial, and I'll also get you a homework for tomorrow. So hopefully the homework will be fun and not too much work.